Space. It calls to us, doesn't it? A vast, dark, beautiful expanse sprinkled with countless stars and galaxies. For millennia, humans have looked up at the night sky with wonder. We dreamed of reaching those distant lights. Today, space travel is not just a dream, it is a reality. We have sent probes to the farthest reaches of our solar system. We have walked on the moon. But how do we do it? How do we navigate this cosmic ocean? The answer, my friends, lies in physics. Understanding the fundamental laws of the universe is absolutely vital. Without physics, space travel would be impossible. It's the instruction manual for the cosmos. These laws tell us how things move, how gravity works, and how energy behaves. They are the invisible strings that orchestrate the dance of planets, stars, and galaxies. When we want to send a rocket to Mars, or a telescope to observe distant nebulae, we must first consult these laws. We need to know how much force is needed to escape Earth's pull. We need to calculate the precise trajectories to reach our destinations, millions of kilometers away. Physics provides the tools, the equations, and the understanding. It's like having a map and a compass for uncharted territory. The universe plays by a set of rules, and physics helps us learn them. Think of launching a rocket. It's not just about pointing it upwards and hoping for the best. That would be a very short and probably quite fiery trip. Engineers and scientists spend years, even decades, applying physical principles. They calculate fuel requirements, structural stresses, and navigational paths. Every single decision, from the shape of the rocket to the timing of the launch, is dictated by the laws of physics. These aren't just abstract theories found in textbooks. They are practical, powerful tools that humanity uses to achieve the extraordinary feat of leaving our home planet and venturing into the great unknown. So as we embark on this journey to understand space travel, remember this: physics is our guide. It's our key to unlocking the secrets of the cosmos. It allows us to turn science fiction into science fact. From the simple act of throwing a ball to the complex maneuvers of a spacecraft docking with the International Space Station, physics is there. It governs every moment, every movement. Understanding these principles doesn't just make space travel possible, it makes it comprehensible. It allows us to appreciate the sheer elegance and power of the universe we inhabit. Let's explore these amazing laws together. Let's start with Sir Isaac Newton, a true giant of science. His first law of motion is often called the law of inertia. It sounds fancy, but the idea is quite simple. An object at rest will stay at rest, and an object in motion will stay in motion, with the same speed and in the same direction, unless acted upon by an unbalanced force. Think about that. If you're sitting on your couch, you'll stay there until something makes you move. Maybe the smell of cookies baking. That's your unbalanced force. In space, this law is king. There's no air resistance to slow things down or friction to stop them. Imagine you're an astronaut and you gently toss a wrench inside your spacecraft. What happens? That wrench will continue to float in a straight line at the same speed you threw it. It won't just stop, it won't fall down, because down is relative in space. It will keep going and going until it hits a wall or another astronaut catches it. That's inertia in action. This is super important for spacecraft. Once a probe is sent on its way to Jupiter and it's outside any significant gravitational pull or atmospheric drag, it can essentially coast for millions of kilometers. It doesn't need to keep its engines firing constantly. This principle is a double-edged sword, of course. While it helps save fuel for long journeys, it also means that if something is moving and you want to stop it or change its direction, you need to apply a force. Spacecraft don't have brakes like cars do. They can't just press a pedal and rely on friction with the road. To slow down, they often need to fire their thrusters in the opposite direction of their travel. This provides the unbalanced force Newton talked about. It's all about managing motion, or the lack thereof, in an environment where things just want to keep doing what they're already doing. So Newton's first law is fundamental to planning any space mission. Engineers calculate how much initial push a spacecraft needs to get going. They also calculate how much force and in what direction thrusters will need to fire to make course corrections, or to slow down when arriving at Mars or the Moon. It's like planning a very, very long trip on an incredibly slippery cosmic ice rink. Once you get gliding, you'll keep gliding. Understanding this helps us navigate the vast emptiness of space efficiently and precisely, making sure our robotic explorers and brave astronauts reach their intended celestial destinations. Now, let's move on to Newton's second law of motion. This one is a real powerhouse, especially for rockets. It connects force, mass, and acceleration. The law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. In simpler terms, the more force you apply to an object, the faster it will speed up, or accelerate. And the heavier an object is, the more force you'll need to get it moving at the same acceleration. The famous equation for this is F equals ma. Force equals mass times acceleration. This is the heart of rocketry. Think about launching a massive rocket into space. These things are incredibly heavy, filled with fuel, equipment, and sometimes people. To get such a colossal mass to overcome Earth's gravity and achieve the speeds needed for orbit, you need an enormous amount of force. This force comes from the rocket engines. The engines burn fuel, expelling hot gases downwards at very high speeds. This expulsion creates an upward force or thrust. The greater the thrust, the greater the acceleration of the rocket, especially when considering its large mass. It's a constant battle between the rocket's engines pushing up and gravity pulling down. The mass part of the equation is also crucial. As a rocket burns its fuel, its total mass decreases. This is a good thing. With less mass, the same amount of thrust from the engines will produce a greater acceleration. So the rocket actually speeds up faster as it gets lighter. This is why rockets are often designed in stages. Once a stage has used up its fuel, it's jettisoned, making the remaining rocket lighter and more efficient. It's like a runner shedding a heavy backpack midway through a race to pick up speed. Every kilogram matters when you're trying to escape Earth's gravity. Newton's second law isn't just for launches, though. It's used constantly during a space mission. When a spacecraft needs to change its trajectory, say, to aim for a different planet or to enter orbit around the moon, it fires its thrusters. The amount of thrust and the duration of the burn are carefully calculated using F equals ma. Engineers need to know the spacecraft's mass and how much they want to change its velocity, which involves acceleration. This law allows for precise maneuvers, ensuring that missions like the Mars rovers land in exactly the right spot, even after traveling hundreds of millions of kilometers. It's physics in precise, powerful action. The third and final of Newton's laws of motion is perhaps the most famous, and it's the bedrock of how rockets work. For every action, there is an equal and opposite reaction. It's a beautiful symmetry that governs interactions throughout the universe. If you push against a wall, the wall pushes back against you with the same force. If you jump off a small boat, you push the boat backward as you move forward. This principle is happening all around us all the time, but it's spectacularly demonstrated when a rocket thunders off the launch pad. It's the universe saying, you can't push something without it pushing you back. So, how does this apply to a rocket? A rocket engine works by expelling hot gas downwards at incredibly high speeds. This downward expulsion of gas is the action. According to Newton's third law, there must be an equal and opposite reaction. That reaction is the upward push on the rocket itself. This upward force is called thrust. The faster and the more massive gas the rocket shoots out downwards, the greater the upward thrust it experiences. It's not pushing against the ground or the air, a common misconception. Rockets work even better in the vacuum of space where there's no air to push against or create drag. Think of letting go of an inflated balloon without tying it. The air rushes out in one direction, the action, and the balloon zips off in the opposite direction, the reaction. A rocket engine is a much more powerful and controlled version of this. It's a continuous series of powerful actions, expelling burnt fuel, creating a continuous powerful reaction, the rocket accelerating upwards. This is why rocket engines are so incredibly noisy and produce so much fire and smoke. They are converting chemical energy into kinetic energy, throwing mass out at high velocity to get that vital reactive push upwards. This action-reaction principle is also used for maneuvering spacecraft once they are in space. Small thrusters, called reaction-controlled thrusters, are placed at various points on a spacecraft. When an astronaut or a computer wants to turn the spacecraft, or make small adjustments to its path, these thrusters fire tiny bursts of gas. Firing a thruster on the left side makes the spacecraft turn right. Firing one pointing forward makes it slow down. Each puff of gas is an action, causing a precise reaction that steers the vessel through the void. Newton's third law, simple, elegant, and absolutely essential for our cosmic voyages. Section 5. Gravity's grand design. The universe's invisible hand. Gravity. It's the force that keeps our feet firmly planted on the ground. It holds the moon in orbit around the Earth, and the Earth in orbit around the sun. It's the architect of galaxies and the conductor of cosmic dances. Sir Isaac Newton didn't just give us laws of motion, he also gave us the law of universal gravitation. This law states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. That's a mouthful, but it means bigger things pull harder, and things farther apart pull weaker. This force is what makes space travel such a challenge initially. We have to overcome Earth's immense gravitational pull to even get into space. But once we're up there, gravity becomes a tool. We can use the gravitational pull of planets to help us steer and accelerate our spacecraft. This is called a gravity assist, or a slingshot maneuver. A spacecraft flies close to a planet, like Jupiter or Venus. As it approaches, the planet's gravity pulls on it, increasing its speed. By carefully calculating the trajectory, we can steal a little bit of the planet's orbital energy to fling the spacecraft towards its next destination at a much higher speed, saving fuel and time. Think of the Voyager probes, launched in the 1970s. They used gravity assists from Jupiter, Saturn, Uranus, and Neptune to embark on their grand tour of the outer solar system and eventually head into interstellar space. Without these gravitational nudges, the missions would have taken decades longer, or required impossibly large amounts of fuel. Understanding gravity allows us to choreograph these intricate cosmic ballets. It's not just about fighting gravity, it's about working with it, using its power to our advantage. The universe provides the pathways. Physics shows us how to follow them. Furthermore, gravity dictates what an orbit is. An orbit is essentially a continuous state of falling. An astronaut in the International Space Station isn't weightless because there's no gravity. Earth's gravity is still quite strong up there, about 90% of what it is on the surface. They feel weightless because they, and the station, are constantly falling towards Earth. But they are also moving sideways very, very fast. So fast that as they fall, the Earth curves away beneath them. They are perpetually missing the Earth. That's what an orbit is, a delicate balance between the forward motion of the spacecraft and the pull of gravity. Section 6. Breaking Free. The Challenge of Escape Velocity. To truly venture out into the solar system and beyond, a spacecraft can't just orbit the Earth. It needs to break free from Earth's gravitational embrace entirely. This requires achieving something called escape velocity. Escape velocity is the minimum speed an object needs to be traveling to overcome the gravitational pull of a celestial body, like a planet or a moon, without further propulsion. It's the speed you need to coast away and never fall back. For Earth, this speed is about 11.2 kilometers per second, or roughly 40,320 kilometers per hour. That's over 25,000 miles per hour. That's incredibly fast. Imagine throwing a ball straight up into the air. The harder you throw it, the higher it goes before gravity pulls it back down. If you could throw it with enough initial speed, that magical escape velocity, it would go up and just keep going. It would escape Earth's gravity altogether and drift off into space. Of course, we can't throw things that fast with our arms. That's why we need powerful rockets. They don't achieve escape velocity instantaneously at launch, but rather build up speed as they ascend through the atmosphere and burn through their stages of fuel. The escape velocity depends on two things: the mass of the celestial body you're trying to escape from and your distance from its center. More massive planets, like Jupiter, have a much higher escape velocity, about 59.5 kilometers per second, because their gravitational pull is stronger. Smaller bodies, like our Moon, have a lower escape velocity, about 2.4 kilometers per second. This is why the lunar module that took astronauts off the Moon in the Apollo missions didn't need to be nearly as powerful as the Saturn V rocket that launched them from Earth. Less gravity means an easier escape. Achieving escape velocity is a critical hurdle for interplanetary missions. Probes sent to Mars, Jupiter, or the outer solar system must all reach this speed relative to Earth. It represents a significant energy investment, requiring immense amounts of fuel and powerful engines. Once escape velocity is achieved, however, the spacecraft can then coast through space, its path primarily influenced by the Sun's gravity and the occasional nudge from other planets if a gravity assist is planned. It's the cosmic equivalent of finally getting enough speed on your bicycle to coast up and over a very big hill, with the universe waiting on the other side. Section 7. Einstein's Revolution, Spacetime and Cosmic Speeds. While Newton's laws are fantastic for most of what we do in space travel within our solar system, when we start talking about very high speeds, close to the speed of light, or very strong gravitational fields, we need to turn to another giant, Albert Einstein. His theories of special and general relativity revolutionized our understanding of space, time, gravity, and the universe itself. These theories have subtle but important implications for space travel, especially as we dream of venturing further and faster. One key concept is that the speed of light in a vacuum is constant for all observers, a cosmic speed limit. Special Relativity, published in 1905, deals with motion at constant speeds. One of its most mind-bending consequences is time dilation. This means that time can pass at different rates for different observers, depending on their relative speeds. If you were on a spacecraft traveling at a significant fraction of the speed of light, time would pass slower for you compared to someone on Earth. This isn't science fiction, it's been experimentally verified. For astronauts on the International Space Station, moving much slower than light speed, the effect is tiny. They age a few milliseconds less over 6 months. But for future interstellar travel, it could be significant. General relativity, from 1915, is Einstein's theory of gravity. It describes gravity not as a force between masses, like Newton did, but as a curvature or warping of space-time caused by mass and energy. Imagine space-time as a giant trampoline. If you place a bowling ball, representing a planet or star, in the middle, it creates a dip. If you roll a marble, representing a spacecraft, nearby, it will curve towards the bowling ball not because the ball is pulling it, but because the fabric of the trampoline itself is curved. This theory also predicts that strong gravity can affect time, making it run slower closer to a massive object. These relativistic effects are crucial for technologies we rely on, like the Global Positioning System, GPS. GPS satellites orbit Earth at high speeds and are further away from Earth's gravitational center. Both special relativistic time dilation, due to their speed, and general relativistic time dilation, due to their altitude in Earth's gravitational field, must be accounted for. If they weren't, GPS calculations would be off by several kilometers each day. For future ultra-precise navigation in deep space, or for missions venturing near massive objects like black holes or neutron stars, if we ever dare, Einstein's theories will be indispensable guides. The universe is stranger and more wonderful than we can often imagine. Section 8. Propelling our dreams. The engines of exploration. To boldly go where no one has gone before, we need ways to move. That's where propulsion systems come in. These are the engines that give spacecraft the push they need to launch from Earth, maneuver in space, and reach distant worlds. For most of space exploration history, we've relied heavily on chemical rockets. These are the workhorses we've discussed, using Newton's third law. They work by burning a fuel, like liquid hydrogen, with an oxidizer, like liquid oxygen, to produce hot gas, which is expelled at high speed through a nozzle to generate thrust. They provide a lot of thrust quickly, which is great for escaping gravity. Chemical rockets are powerful, but they have limitations. The main one is that they require a lot of fuel. Fuel is heavy, and the more fuel you need to carry, the heavier your rocket becomes, which means you need even more fuel to lift that extra fuel. It's a bit of a frustrating cycle. This limits how fast we can go and how much we can carry on long-duration missions to the outer solar system or beyond. So scientists and engineers are always looking for more efficient ways to propel spacecraft through the cosmos, using less fuel to get more oomph, or more technically, a higher specific impulse. One such advanced propulsion system already in use is ion propulsion. Ion engines work by accelerating charged particles, ions, using electric or magnetic fields and expelling them at extremely high speeds, much faster than the exhaust from chemical rockets. They produce very little thrust, like the gentle push of a piece of paper resting on your hand. But, and this is a big but, they can operate for very long periods, months or even years, continuously accelerating the spacecraft. This gentle but persistent push can eventually lead to very high speeds, making them ideal for long, deep space missions where fuel efficiency is paramount. Missions like Dawn and Deep Space One have successfully used ion drives. Looking further ahead, scientists are exploring even more exotic concepts. Solar sails, for instance, would use the pressure of sunlight itself to push a spacecraft, like a sailboat uses wind. Nuclear thermal propulsion could use the heat from a nuclear reactor to superheat a propellant like hydrogen. offering much higher efficiency than chemical rockets. There are even more futuristic ideas like fusion rockets or Bussard ramjets. Each of these relies on understanding and harnessing different physical principles. The quest for better propulsion is a quest for a deeper understanding of physics, pushing the boundaries of what's possible in our exploration of the universe. Section 9. The future is stellar physics guiding our cosmic journey. The journey of space exploration has only just begun. We've taken remarkable first steps from Yuri Gagarin's pioneering orbit to the rovers diligently exploring Mars. But the universe is vast, and our ambitions are growing. We dream of sending humans to Mars, establishing bases on the moon, and perhaps one day venturing to the stars themselves. To achieve these grand visions, our understanding and application of physics will continue to be absolutely crucial. It is the bedrock upon which all future space endeavors will be built. Every new discovery in physics has the potential to revolutionize how we explore the cosmos. Consider the challenges ahead. Long-duration human spaceflight to Mars will require us to better understand and mitigate the effects of cosmic radiation and prolonged weightlessness on the human body. Problems deeply rooted in physics and biology. Developing faster and more efficient propulsion systems, perhaps moving beyond the limitations of chemical rockets to things like advanced plasma drives or even speculative warp drives, if the physics ever allows, will be essential for reducing travel times and opening up more of the solar system. This requires breakthroughs in our understanding of energy, matter, and possibly even space-time itself. Physics will also guide our search for life beyond Earth. Understanding the conditions under which life might arise on other planets and moons, the presence of liquid water, a stable energy source, the right chemical ingredients, is all based on physical and chemical principles. Telescopes like the James Webb Space Telescope are peering into the atmospheres of exoplanets using spectroscopy, the study of how light interacts with matter, to search for biosignatures. This is physics enabling us to ask and perhaps one day answer one of humanity's oldest questions. Are we alone? The future of space travel is inextricably linked to the future of physics. As our knowledge deepens, so too will our capabilities. New theories, new experiments, and new technologies born from physical insights will unlock new destinations and new possibilities. The universe is a laboratory, and physics provides the tools for experimentation and discovery. The same curiosity that drove Newton and Einstein continues to drive us today. The stars are not just distant lights, they are destinations, and physics, our faithful guide, will continue to light the way, helping us to reach for them and understand our place in this magnificent grand cosmos.